Hey everyone, and welcome. Today, we are diving deep into the invisible language that literally powers our entire modern world: signals and systems. From the music you're streaming right now to the vital signs on a hospital monitor, it's all built on these core ideas. So, let's jump right in.
So, to get our minds warmed up, I've got a question for you. I want you to think about three things that seem totally unrelated: the rumble of an earthquake, an invisible radio wave carrying your favorite song, and the steady beat of your own heart. What on earth could possibly connect all three of those?
Well, the answer is actually pretty simple. They are all signals. Every single one is a way of carrying information through some kind of change or variation. And this very concept, the signal, is really the hero of our story today.
Okay, so that brings us right to our first stop. We're going to break down exactly what we mean when we use these two massive words: signals and systems.
A signal, at its core, is just information in motion. It's some physical thing that changes over time or through space to carry a message. Think about the sound wave coming from your headphones. The air pressure is constantly varying, right? Well, that specific variation is what's carrying the music to your ears. That's the signal.
Right. So if the signal is the message, then a system is the message processor. It's anything that takes in a signal, does something to it, maybe it modifies it, or amplifies it, or filters out noise, and then spits out a new signal. Your radio is a perfect system. It takes in a radio wave signal, and its output is the sound signal you hear.
Okay, so now that we know what a signal is, let's get a bit more organized. Because not all signals are created equal. We can actually classify them into four main types. Think of this next part as a field guide for the information age.
So the first way we can sort signals is by looking at time. A continuous time signal, well, it exists at every single instant. It's like a smooth, unbroken ramp. A discrete time signal, on the other hand, only exists at specific, separate moments. It's more like a set of stairs. You have a value on each step, but there's nothing in between them.
The second way we can classify them is by their value, or what we call their amplitude. Think of it like a dimmer switch versus a regular light switch. An analog signal is like that dimmer. It can take on any brightness level in a smooth, continuous range. But a digital signal, that's the light switch. It's stuck with a few specific values, like just on or off.
And this clock example is the perfect way to see the difference. An old-school analog clock, the second hand sweeps smoothly around, passing through every single possible position. That's analog. But a digital clock, the number just snaps from 02 to 03. There's no 02 and a half. That jump is digital.
So, when we combine these two ways of classifying, we get our four types. First up, the continuous analog signal. You can see it right here. It's a smooth, flowing curve. It's defined at all points in time, and its value can be anything along that curve.
Next, we've got a continuous digital signal. Now, notice it still exists across all of time, just like the last one. But look at its amplitude. It's restricted. It can only be +5 or -5, nothing else. It just jumps between those two levels.
Now things get interesting. This is a discrete analog signal. Here, the signal only exists at those specific points in time, at 1, 2, 3, and 4. But at those specific moments, its value, the height of that line, could theoretically be anything in a range.
And finally, we have the absolute workhorse of all modern technology, the discrete digital signal. It only exists at specific times, and its value can only be one of a few specific levels. This is the bedrock of everything from your computer to your phone. This is why your phone can store thousands of songs, while an old analog vinyl record could only hold a dozen or so.
All right, so we've sorted signals by time and by their value. But there's another really important way to think about them. Can we predict what they're going to do next? And this leads us to the idea of deterministic versus random signals.
So a deterministic signal is one you can describe perfectly with a math equation, a simple sine wave, for example. If you know the formula, you know its exact value anywhere in the past, present, or future. But a random signal, well, that's like the static on a radio or the ups and downs of the stock market. You can't predict its exact value. There's uncertainty baked in. You can only describe its general behavior using statistics.
Okay, so we know what signals are, we know how to classify them, but how do we measure them? How do we put a number on their strength or their impact? That's where two really important concepts come in: energy and power.
Now you're looking at some formulas here with some scary-looking symbols, but don't panic. We are not getting bogged down in the math today. The big idea is what's important.
Energy measures the total impact of a signal over its entire lifetime, while power measures its average intensity or its sustained strength over time.
And this leads to a really useful distinction. An energy signal is something that has a finite, measurable amount of total energy. Think of a single clap. It's a burst of energy, and then it's gone. So its average power over all of time is basically zero. A power signal, though, is something that goes on forever with a constant, finite average power, like the steady 60 Hz hum from a power line. Its total energy would be infinite because it never stops.
And here's a super handy rule of thumb that connects these ideas. Any signal that is periodic, meaning it just repeats the same pattern over and over forever, is a power signal. It has to be, right? Because it goes on forever, its total energy is infinite, but its average power over any one of those repeating cycles is finite. You know, that last point about repeating patterns is the perfect way to get into our final section. Let's take a closer look at what it actually means for a signal to be periodic.
So the official definition is right here. A signal, which we'll call x of t, is periodic if its value at any time t is the exact same as its value a little bit later, at time t plus some fundamental time period t naught. All that really means is if you shift the signal by exactly its period, it lays perfectly on top of itself. It repeats.
This brings up a really cool question. Let's say you take one periodic signal, like a nice, simple sine wave, and you add it to another periodic signal that has a different period. Is the final combined signal guaranteed to also be periodic?
Well, you'd think so, but the answer is no. And the rule for why is just fascinating. The combined signal is only periodic if the ratio of the two original periods is a rational number. You know, a simple fraction like 7/5. If that ratio is an irrational number, something weird like 1 over the square root of 3, the resulting wave will actually never, ever perfectly repeat itself. It will go on forever without finding a pattern.
So there we have it. We've built a whole toolkit for understanding and classifying the language of signals. But really, this is just the beginning. The real magic, the stuff that drives all of modern engineering, happens when we ask the next question. How do we design the systems, the filters, the amplifiers, the processors that can actually take these signals and transform them to create everything from noise-canceling headphones to life-saving MRIs? And that is a story for another day. Thanks for joining me.